Last set of notes for the year. So we're in section 10.8. We're talking about graphs of polar equations. So what we're doing, what we want to do today is just take a look at how we go from plotting points. We talked about how we plot points in polar coordinates. We want to graph an entire equation. So we'll do an easy one. We'll do an easy one with just making a table of values, and then we'll look at using our calculator. So let me grab this, and we're going to plot an equation. So the example we're going to do is we want to plot r equals 3 cosine theta. And to do it by hand, not really difficult. It's just a little, because it's not like we don't have an idea of what these look like yet. So we're going to make a table of values. We're just going to do r and theta, and we're just going to plug in a bunch of values for theta and figure out r. So we're going to start with the easy one. We'll just start going around the circle. So when theta equals pi over 6, we're going to take cosine of pi over 6 times 3. Well, the cosine of pi over 6 is square root of 3 over 2. So r is 3 square root 3 over 2, which is about 2.6 if we calculate it out. If r equals pi over 4, cosine of pi over 4 is square root of 2 over 2. So we get 3 square root 2 over 2, which is about 2.1. If r equals pi over 3, we're just plugging in the values that we know from the unit circle. Cosine of pi over 3 is 1/2. So r is 3 times 1/2, or 3/2, or 1.5. When we plug in pi over 2, cosine of pi over 2 is 0, so we just get 0. And I'm going to go around a little further, 2 pi over 3. And I'm just going to, these start repeating now, and we end up with negative signs. So I'm not going to go through each calculation. This comes out to minus 3/2, or minus 1.5. We end up at 5 pi over 6. We end up at minus 2.6. And I'm getting these just by plugging theta in here and calculating. 5 pi over 6 pi, we get negative 3. At 7 pi over 6, we get negative 2.6. At 3 pi over 2, plug that in, and we get 0 again. And we'll plug in a couple more. At 11 pi over 6, we get 2.6 again. And at 2 pi, we get 3. So now we're just going to plot. We're going to plot all these points on our polar graph here. So at pi over 6, here's pi over 6. Our radius is 2.6. So 1, 2.6. So our radius is going to be about here. So I just went up to pi over 6 and out 2.6. At pi over 4, I'm at about 2.1. So I'm going to go up here to pi over 4. And I'm at 2.1. So I'm about here. At pi over 3, I'm at 1.5, so here's pi over 3, and I'm at 1.5, so I'm here. And at pi over 2, here at pi over 2. I'm down here at 0, so I'm at the origin. Everybody see how I'm getting my points, how I'm plotting my points? This is from what we did on Friday. So now at 2 pi over 3. When I go to 2 pi over 3, I end up at 2 pi over 3 is can't read my graph. So at 2 pi over 3, we're here. And our radius, so I'm going to 2 pi over 3, and our radius is negative 1.5, so I'm going here, and I'm going to go the other direction. So my 2 pi over 3 is here, my radius is negative 1.5. So I'm here. At 5 pi over 6, I'm here, and my radius is negative 2.6, so I'm going out to here. Did I do that right? 5 pi 6, yeah. And at pi, my radius is negative 3, so here's pi, and my radius is negative 3. And as I go out to 7 pi over 6, we see that my values start to repeat. So my graph just looks like so. So this graph is a circle. So the graph of r equals 3 cosine theta is a circle. Just plotting my points, come up with a table of values, plot my points, and I end up with a circle. Everybody see how we plotted the points? We just did over and over what we did at the very beginning of the lesson on Friday. Now let's look at how we converted this. Just really quickly, I want to look at converting this to rectangular coordinates. What we did a similar example on Friday. What we did was multiply both sides by r, because we know that r cosine theta is x. So if I multiply both sides by r, I get r squared equals 3r cosine theta. So, and r squared is x squared plus y squared equals 3x. And I said that if you got to here, that this would be fine to convert this equation. I just want to go a little further to show where this circle comes from. So I'm going to subtract 3x from both sides. X squared minus 3x plus y squared equals 0. We're going to go ahead and complete the square here. So x squared, 3 halves, we end up with minus 3 halves. So we add 3 halves squared. And we're going to add 3 halves squared to, we have the plus y squared here. And this, we add 3 halves to the other side, equals 3 halves. And I'm just going to leave it written as 3 halves squared. This is a perfect square now. X squared minus 3 halves squared plus y squared equals 3 halves squared. So and then I'm just going to rewrite this x minus 1.5 squared plus y squared equals 1.5 squared. So we have a circle centered at 1.50 with a radius of 1.5. So here's my circle. Center is here at 1.5, and its radius is 1.5. So that's how this turns into a circle. Questions? So let's talk about how we do these graphs the easy way now. This is the harder way, plotting points on our polar graph. You need to be, and all we did here is plug in points for theta, plug in values for theta, and we used easy values, pi over 6, pi over 4, pi over 3, pi over 2. all of our values that are on our graphs, found a value for the radius, and plotted points. So not difficult, just a little tedious. Let's take a look at the easy way. On your calculator, let me clear this out, and we're going to clear this. On your calculator, if you go to mode, and down here where it says function, PAR, POL, and SEQ, you're going to go down and change this to, this third one, POL, is polar. So we change this to polar. And I want to make sure I'm set in radians. I don't want to be in degrees. I want to be in radians. And we're going to, let me make sure I do this, hit enter, and then let me make sure I get over to polar here, hit enter there. So now we're in radian mode and we're in polar mode. So when I go to y equals, instead of x it says r equals. And my variable now is going to be theta. So for this last equation that we just graphed, we can say 3 cosine theta, and we're going to graph that, and there's my graph. And if you look at zoom, we go to zoom trig, zoom 7, and it gives a nice window for graphing trig functions. So there's the graph of r equals 3 cosine theta in your calculator. So you set it in polar and graph it in your calculator. Yeah, make sure your calculator is in radian mode and you set your graph to polar. If you put it in degree mode, it gives you a funky graph. You end up with lines, yeah. Are they the small ones? Are they AAAs? All we have are the big ones, so I don't think we have any for the TIV3s anymore. They got all used this year. When you you might have, I bet you have your stat plots on. So go to, let's see, how do we do that? Go to second, whoops. For sure, I got it. And you want to turn those off. It probably is trying to graph something from a table of values. So let's look at a couple of these graphs, a couple of graphs in your calculator. So let's graph, I'm going to graph in the calculator, let me clear this, 2 minus 2 sine theta. 2 minus 2 sine theta. So we'll graph that. And we get this shape. This is called a cardioid. And we'll talk a little bit more about these special shapes. This is called a cardioid because it's kind of heart-shaped. So 2 minus 2 sine theta is a cardioid. Let me graph a r equals 1 plus 2 cosine theta. R equals, let me clear that out, 1 plus 2 cosine theta. And we want to graph that. So this one is called a limosome. And the cardioid is a limosome also. It just, that one just had a dimple instead of a loop. So we can get all kinds of, interesting graphs from polar equations. Let's look at r equals sine of, oops, let me clear that, sine of 3 theta. So sine 3 theta, and we'll graph that. This is called a rose curve. So we end up with a rose curve. If we graph y equals cosine, let's do cosine of 4 theta. And we want to graph that one. There's another rose curve, but it has more. Let's zoom in a little bit. Zoom in, zoom 2. So there's our rose curve, cosine 2. Did we do 2 or 4? 4 theta. So this is another rose curve. So we get all kinds of interesting graphs. Yeah. Is your calculator set in radian mode? Make sure it's in radian. Did you get it, Dylan? No? Are you in, did you do Zoom Trig? What's that? I think so. Zoom. Yeah, do Zoom 7. Now zoom in. Oh, is your batteries are your batteries dying? Your screen's really dim. All right, so we get all these interesting curves. So let's talk about what they're named. I don't know how I did that. I'm gonna do that. So special polar graphs. We talked about circles. When we have r equals a cosine theta, we get a circle that's on the x-axis. When we have r equals a sine theta, we get a circle on the y-axis. Now these diagrams are in your book on page 760. What you need to do, what I would like you to do for the test is just be familiar with, if I said, for example, if you had a multiple choice question and it said, identify the lemniscate. This is a lemniscate. Identify the lemniscate. Just know what a lemniscate looks like. I'm not going to ask you to graph it or to be able to go from the equation to the graph, something like that. You can do it in your calculator. But I just want you to know the names of some of these special graphs. So this figure 8 is called a lemniscate. And we have a r squared and some function of sine or cosine. So before, when we simplified that equation and it came up to r squared equals something, that's why we didn't necessarily need to simplify it, is this r squared equals something, when it's in this form, gives us this graph called a lemniscate. Lemniscate is a circle 8. Looks like an infinity sign. Yep. We graphed a couple of these already. These are all called limasones. And the cardioid and the loop, the one with the loop, is just different kinds of limasones. Limasones all have the equation r equals some number plus or minus sine theta or cosine theta. Sometimes we get a loop with a limasone. Sometimes we just get a dimple with a heart shape. Sometimes we just get just a little going in, and sometimes it's just kind of flat on that side. But those are all limasones. And the cardioid is a special name for a limasone. But these are the circles, the lemniscates, and the limasones are the kind of the standard polar graphs. So on page 760, they have a table that has all of these. It looks just like this. Just be familiar with what shape is a limasone, what shape is a lemniscate, what shape might give you a circle. But you'll have your calculator, so you know how to graph these in your calculator now, so you can verify. Just know what a lemniscate is and what a limasone is. Oh, and then we still have the rose curves. So there are the rose curves. The rose curves are just going to be sine or cosine of some multiple of theta. We did 2 theta and we did 4 theta. if n is odd, if the number we're multiplying in front of theta is odd, we get that number of petals. If n is even, we get twice that number of petals. So those are our rose curves. So circles, lemniscates, limasones, and rose curves. And this table's on page 760 of your book. But it's polar equations, when you graph them, it's interesting how many different unusual things you come up with. Any questions on graphing polar equations? All right. Homework. This is your last homework assignment other than your project. There is a review for the test, though. Page 762. All right, there you go. If you're having trouble with your